Welcome back. Well, students, before starting with hybridization, we'll see a theory on which hybridization shape of the hybrid orbitals is based. We call it valence shell electron pair repulsion theory. Many a time it is abbreviated as VSEPR. Well, as the name suggests, this theory basically deals with the repulsion between the pair of electrons of the valence shell. And since it comments about the repulsion, it basically helps us in predicting the shape of a particular molecule. Well, according to this theory, the repulsion among two lone pair pairs is maximum repulsion among a bond pair and a lone pair electrons is moderate and repulsion among two bond pairs is minimum. So although we say that repulsion among two bond pairs is minimum, but it is there. And whenever there is a repulsion, it always increases the energy of the molecule and it destabilizes the molecule. Higher the energy, lesser will be the stability of the molecule. So molecule, they acquire a shape whereby they tend to minimize their repulsion, they tend to minimize their energy. So the shape of a molecule basically depends on the lowering of energy. The shape in which the energy is lesser is the shape in which the stability of the molecule is higher. So that will be the more stabilized shape of that molecule. So we'll start with hybridization. Well, hybridization, we'll see what is hybridization. Well, I would like to tell you one thing, that as far hybridization is concerned, it is purely hypothetical concept. It is a hypothetical concept. People, they observed the shape of certain molecules and on the basis of those shapes, they predicted certain things. And they gave us the concept of hybridization. According to this concept, two or more atomic orbitals, they combine together to form the same number of hybrid orbitals. For example, if I talk about S subshell is spherical. And if I talk about P is doubled. When S and P, they combine together, they lead to the formation of this type of orbital. This is a hybrid orbital. So here you have S, here you have P. This is sp hybrid. And how many hybrid orbitals I'll get? Two hybrid orbitals I'll get. The number of hybrid orbitals you'll get is always equal to the number of orbitals which are taking part in hybridization. So here you can see that two orbitals, they are taking part in hybridization. One is S, then another one is P. So when two orbitals are undergoing hybridization, that will lead to the formation of two hybrid orbitals, two hybrid sp hybrid orbitals. So this is what you are getting. So this is what hybridization is. It is a hypothetical concept. According to this concept, two or more atomic orbitals, they combine together to form the same number of hybrid orbitals which are intermediate in length and strength. Neither they are so strong as S, nor they are so weak as P. Neither they are so small as S, nor they are so large as P. So this is what hybridization is. Unlike your textbook, here I am dividing hybridization into 3 parts and I'll be taking them individually. So those means it is not given like this in your textbook. So unlike your textbook, I'll divide them in 3 parts. We'll take all these 3 parts, and in these 3 parts, all hybridization will get included, which are there in your syllabus. Because some of the hybridization like DSP2, D2SP3 hybridization, they are not in 11th standard, they are in 12th standard. So we'll take them when I'll give you a lecture of 12th standard. So first I'll tell you hybridization in which all unpaired electrons takes part. So hybridization in which all unpaired electrons take part. In this first I'll tell you sp hybridization. And when I talk about sp hybridization, I'll talk about a very familiar compound, that is beryllium chloride, BeCl2. Now let us have a look at beryllium. I taught you this thing earlier, that beryllium has got 2 electrons in the s. One of the s electron get excited and it jumps to the p subshell, leading to the formation of 2 unpaired electrons, that is one in the s and one in the p. So here you have got 2 unpaired electrons. I am teaching you the hybridization in which all unpaired electrons they take part. Now how many unpaired electrons you got? 2, and these 2 unpaired electrons they will take part in hybridization. So how many hybrid orbitals you will get? 2, as you can see in this. In this structure you can see 1 s and 1 p is undergoing hybridization. So that will lead to the formation of 2 hybrid orbital, 2 sp hybrid orbital. Now the question comes, if I have got 2 hybrid orbitals, how they will be placed? Suppose this is beryllium. This is one of the hybrid orbital with an unpaired electron. What about the another hybrid orbital? That will be just opposite to each other. Here I am just explaining you by the help of 2 markers. Say they are representing 2 bonds. So in order to represent these 2 bonds, if these 2 bonds they have to have minimum repulsion, they have to be just opposite to each other. That is 180-degree angle. If the angle is lesser than 180, they will experience repulsion. If the angle is more than 180, then also they will experience repulsion. So the minimum repulsion will be when they are at an angle of 180 degree, that is linear. So if one of the hybrid orbital is like this, the another hybrid orbital can be drawn like this. Now these unpaired electrons, they will get overlap. Let us have a look at the configuration of chlorine also. Chlorine has got 2 electrons in the s, and chlorine has got 5 electrons in the p. 1, 2, 3, 4 and 1, 5. This unpaired electron of chlorine is overlapping here. So you are getting a bond. Likewise here also, the unpaired electron of chlorine is overlapping like this. So you are getting a bond here. So this is how beryllium chloride molecule is. So if you have beryllium here, you'll have single bond chlorine, and you will see the bond angle is of 180 degrees and the structure is linear. So dear student, whenever you have got sp hybridization, please do remember that the symmetry is linear, the shape of the molecule is linear. Now let us talk about another hybridization, that is sp2 hybridization. When I am talking about sp2, I am basically dealing with a compound that is BF3. Let us have a look at boron. Boron has got 2 electrons in the s, and boron has got 1 unpaired electron in the p. One of its electron will jump to p, leading to the formation of 3 unpaired electrons. I am removing this electron, so you will get 3 unpaired electrons. These 3 unpaired electrons, they will undergo hybridization, and the hybridization is sp2. That is, 1 orbital of s is combining with 2 orbital of p. That's why it is sp2. If 3 orbitals are undergoing hybridization, we'll get 3 hybrid orbitals. So when 2 orbitals they undergo hybridization, you get 2 orbitals, and as far as the shape of 2 orbitals were concerned, it was like this, linear. Now when I'm saying 3 orbitals are undergoing hybridization, that means 3 hybrid orbitals will be formed. If I talk about the third hybrid orbital, the third hybrid orbital will make a bond like this. When it will make a bond like this, these two will bend like this because you have got bond pair repulsion. So the structure will be somewhat like this, trigonal. Initially it was linear. When the third bond is formed in the same plane, these two bonds, they'll experience repulsion, they'll bend. So you'll get a structure like this, that is trigonal planar. So if we draw a structure of boron trifluoride, it is like this. Here you have boron, one hybrid orbital, second hybrid orbital, third hybrid orbital. You got one electron, second electron, third electron. Here it is overlapping with the unpaired electron of fluorine. Like chlorine, fluorine also has got an unpaired electron in its valence p subshell. Here also you have got unpaired electron. Here again you have got unpaired electron. So if boron is here, this is one of the BF bond. This is another BF bond, another BF bond. The bond angle in this case is 120 degrees and the shape, if you see, is trigonal. So here in this case we say that the shape is trigonal planar. So BF3 is trigonal planar. Next we'll see another molecule and next different type of hybridization, that is sp3. All alkanes, they are always sp3 hybridized. All alkanes, in all alkanes, carbon is sp3 hybridized. So here we'll see a molecule that is CH4. Carbon has got 2 electron in the S. Carbon has got 2 electron in the P. Again, one of the S electron will jump to P and you will have 4 unpaired electrons. Now, the hybridization which we are doing here is the hybridization in which all unpaired electrons they take part. You have got 4 unpaired electrons. All these 4 unpaired electrons are taking part in hybridization, and that hybridization is sp3. That is 1 orbital of S and 3 orbital of P are combining. So the hybridization is sp3. Dear students, how many orbitals they are undergoing hybridization? 4. 1 of S and 3 of P. I taught you that the number of hybrid orbitals is always equal to the number of orbitals undergoing hybridization. So if 4 orbitals are undergoing hybridization, resultant orbital will be 4. Now the question comes to our mind, how these 4 orbitals they will be arranged in 3-dimensional structure, or 3-dimensionally how they will be arranged. I taught you that in sp the shape is linear, minimum repulsion at 180. Then in sp2 the shape was like this, trigonal planar. It was like this, trigonal planar. Now the question comes to our mind, what about the 4th bond? Here the hybrid orbital will be 4. The possibility is that the 4th orbital will come in the same plane. If it will come in the same plane, this one will bend and the shape will become somewhat like this. That is a square planar, like this, a square planar. So one symmetry which is possible is square planar. So what I can say that CH4 can exist like carbon in the center, one hydrogen, one hydrogen, one hydrogen, one hydrogen. In this, the bond angle is of 90 degrees. So it can be square planar. So it can be square planar. But we have got another symmetry also, which is possible. And I'll tell you how that is possible. Again, this is linear. Then we have got trigonal, which is like this. I taught you that the 4th orbital will come in the same plane. So it will become square planar. But the second possibility is that it will not come in the same plane. It will come perpendicular to the plane, like this. If it will come like this, these three orbitals will experience repulsion. If the fourth bond is coming like this, you have bond pair repulsion. So there will be a repulsion between this bond and these three bonds. So these three bonds, they will bend in the opposite direction, that is towards me. So they'll bend like this and you'll have it like this. So it is like this. If you take it like this, you'll see a tetrahedron. So you'll see a tetrahedral structure. This is the tetrahedral structure you have got. So tetrahedral structure can be drawn like this. 1, 2, 3 and 4. So for CH4 we have got two possible symmetries, that is square planar and tetrahedral. Which of them is possible? Well, in tetrahedral, the bond angle is nearly equal to 109, that is 109.25 degrees we say. Now you can see that in this structure, this is a tetrahedral structure. In tetrahedral structure, the bond angle is more than 90 degrees. The higher the bond angle, the lesser will be the repulsion. And the lesser the repulsion, the more will be the stability. That means tetrahedral structure is more stable than square planar structure. So square planar will not exist. It is tetrahedral which will exist. So if we have a carbon atom here, this is one of the hybrid orbital, second hybrid orbital, third hybrid orbital and fourth hybrid orbital. All these four hybrid orbitals will have unpaired electrons. And these unpaired electrons will overlap with the unpaired electron of hydrogen. Hydrogen I am drawing like a sphere because it has got only S subshell. So you are getting 4 bonds. So CH4 is tetrahedral. This is your textbook exercise question. In that it is asked that the two possible structures for CH4 molecule are square planar and tetrahedral. Give reason why CH4 is not square planar but it exists as tetrahedral. The answer is that in square planar the bond angle will be 90 degrees. That means there is a prominent repulsion between hydrogen atoms. Higher the repulsion, more will be the energy, lesser will be the stability. Whereas in tetrahedral, the bond angle is nearly equal to 109 degrees. That means the repulsion is lesser. Lesser the repulsion, lesser will be the energy and higher will be the stability. So this is what happens in CH4 molecules. After this, we'll move on to the next hybridization. And the next hybridization is sp3d1. In this we'll see PCl5 molecule. If we have a look at phosphorus, it has got 2 electron in the S and it has got 3 electron in the P, 3 unpaired electrons in the P. It has got a weakened D subshell also. So what will happen? One of the S electron will jump to D. It will not come to P because P is already half-filled and stable. So one of the S electron will jump to D, leading to the formation of 5 unpaired electrons. So in phosphorus we have got 5 unpaired electrons and I am teaching you the hybridization in which all unpaired electrons take part. If we have got 5 unpaired electrons, all these 5 unpaired electrons will undergo hybridization and they will lead to the formation of 5 hybrid orbitals. So the hybridization is S1P3D1, that is sp3d1. Dear students, I taught you that when the hybridization is sp2, the shape is like this, trigonal. In sp3, one of the bond came perpendicular. Now in sp3d1, one of the bond will come like this, the other one will come from the opposite plane. So these 3 bonds, they will remain in their plane. They will remain like that only. They will not bend in either of the side. So if I got phosphorus like this, and here I've got 1, 2 and 3 bond with chlorine, chlorine, chlorine. One of the chlorine will come from here, it will form a bond this side. Another chlorine will come from the opposite side, it will form a bond like this. These bonds, they are known as axial bonds. Axial bonds. And these bonds, they are equatorial bonds. So you have two different type of bonds, that is axial bonds and equatorial bonds. If I connect these chlorine atoms like this, you'll see a triangle and you'll see a pyramid like this. Likewise, you'll see a pyramid on the opposite side also. That's why its shape is trigonal bipyramidal. The shape is trigonal bipyramidal. Dear students, you have to remember one thing, that the axial bonds are always longer than the equatorial bonds. It is because when you have three bonds in one plane and one of the chlorine is coming to form a bond with these three, with phosphorus, these three chlorines which are there in the same plane, they will repel it. They will repel the incoming chlorine atoms on the axis. They will experience repulsion. That's why the bond will become longer. They'll move away. That's why the axial bonds, they are longer and the equatorial bonds, they are smaller. Again, the chlorine atoms which are at the equator will experience repulsion. They will give repulsion to the chlorine which is coming through axis. And that's why the axial bonds, they are longer and weaker. Now, since the axial bonds are longer and weaker, that's why PCl5 very readily breaks into PCl3 and Cl2. So this is how PCl5 it appears, that and the shape is trigonal bipyramidal. Next we'll see another hybridization, that is sp3d2 and the compound is SF6. Let us have a look at electronic configuration of sulfur. It has got 2 electrons in the S and has got 4 electrons in the P. 1, 2, 3 and the fourth one is here. It has got a weakened D subshell also. So this is the weakened D subshell you got. One of the electron from the P will jump to D. So you'll have one unpaired electron. One of the S electron will also jump to D. You will have another unpaired electron. So total number of unpaired electron is 6. Again, we are doing the hybridization in which the number of hybrid orbital is always equal to the number of unpaired electron. All unpaired electrons, they are taking part in hybridization. Now 6 electrons, 6 unpaired electrons we have got, which are taking part in hybridization. So how many hybrid orbital will get? 6. That is 1 from S, 3 from P and 2 from D. That is sp3d2. Again the question comes, if you have got 6 orbitals, how they will be arranged? Well, as far axial bonds are concerned, which you can see in this molecule, as far axial bonds are concerned, they are always 2. Rest all the bonds, they have to enter the equator. In PCl5, you have got 3 equatorial bonds. In SF6, you will have 4. The fourth one will enter the equator. That means if you got sulfur here, you will have 1 fluorine, 2 fluorine, 3 fluorine and 4 fluorine. 1, 2, 3, 4. Fifth fluorine and sixth fluorine. Now again we'll see the shape of this molecule. If I connect these fluorine atoms, I'll get a square like this. I am connecting it like this. This is the shape I have got. Well, in this case, I'll tell you one thing. If you have a look at this part, here you are getting a face. This is one face you have got. This is second face you have got. So on the top, you are getting 4 faces. Likewise, here again you are getting one more face. And a face is opposite to this. So 4 face on the top and 4 face on the bottom. So total number of faces are 8. That's why the shape is octahedral. And in this also, the axial bonds are longer and weaker. The equatorial bonds are smaller and stronger. That's why SF6 has a prominent tendency of dissociating into SF4 and F2. Again, the shape is octahedral, the axial bonds are longer, that's why they are weaker, and that's why SF6 has a prominent tendency of dissociating into SF4 and F2. In the first type, we have got the last hybridization, that is sp3d3, and the example is IF7. Now let us have a look at iodine. Like all other halogens, iodine has got 2 electrons in the S and has got 5 electrons in the P. 1, 2, 3 I am drawing here. It also has got a vacant D subshell. 1, 2, 3, 4 and 1, 5 vacant D subshell. So this is S, S2, P5 and D is vacant. So 2 electrons from the P will jump to D. 1 from S will jump to D. That will lead to the formation of 7 unpaired electrons. All halogens in their valence shell have 7 electrons, and here in this case, in iodine, the paired electrons are getting unpaired, the electrons are jumping to the vacant D subshell, so all 7 electrons have got unpaired. We are doing hybridization in which all unpaired electrons they take part. We have got 7 unpaired electrons, all of them will take part in hybridization, so we'll get 7 hybrid orbitals. And that's why the hybridization is sp3d3. Again, the axial bonds will be 2. If a bond is getting added, it has to get added to the equator. So here also, if I have iodine like this, I'll have a fluorine 1, 2, 3, 4, 5. 1 fluorine, 2nd fluorine, 3rd fluorine, 4th fluorine, 5th fluorine, and 2 fluorine atoms on the axis. So one is here, another one is here. We'll see the shape of this molecule. If I connect these fluorine atoms, you'll see we are getting a pentagon. So I'm getting a pentagon. If I connect these fluorine atoms, I'll get a pyramid on the top, pentagonal pyramid. Likewise, a pyramid I'll get on the bottom also. Here I'll get this pyramid. And that's why the shape is pentagonal bipyramidal. Pentagonal bipyramidal. And IF7 again has a prominent tendency of dissociating into IF5 and F2. Because the axial bonds, these bonds, they are longer and weaker. So they will dissociate quickly and IF7 will get converted to IF5 and F2. So with this, we have finished up first type of hybridization, that is hybridization in which all unpaired electrons they take part. We have done sp3, sp3d2. I'll show you. We started with sp, then sp2. In sp we did BeCl2, sp2 BF3, sp3 CH4, sp3d1 PCl5, sp3d2 SF6, and sp3d3 IF7. So here we have finished up with first type of hybridization. Before starting with second type of hybridization, I will teach you sigma and pi bond. But that will not do in this lecture. We'll be doing that in the next lecture. That's all for today's lecture. Thanks for watching. Do subscribe my channel to get all the lectures on time. Any doubt anywhere, you are always most welcome. You got my number on the screen. Send me a message and I'll send you the answer for that. Thanks a lot. Thanks for joining.